This is Computer Organization and Architecture course. And today in Chapter 3, we will discuss arithmetic for computers. So we will check the operation on integers. We will talk about the additions, the addition of binary numbers, the subtraction of binary numbers, multiplication and divisions as well. And then we will talk about dealing with overflow. That's the first major point that we are going to discuss in this chapter. And the second one is the floating point real numbers. We will check the representation first, and then we will investigate the operations, and we will focus only on the addition and multiplication of the floating point real numbers. So we will start with the integer addition. This is an example of adding the binary number 7 and 6. The oggend is 7, as you can see here, and the addend is 6. And when you add two binary numbers, here we take example of 6-bit representation in the example. And if you add 0 plus 1, and if you assume the first carry n is 0, then you add 0 plus 1 plus 0 is equal to 1. Carry 0. So there is no carry. So this will be moved to the next bit position. It's going to be 0. Now 0 plus 1 is equal to 0, carry 1. And this one will be moved to the next position. Similarly, 1 plus 1 plus 1 is 1, carry 1. 0 plus 0 plus 1 is 1, carry 0. And 0 plus 0 plus 0 is 0, carry 0. And that's the last bit position, or the most significant bit in this representation. So 0 plus 0 plus 0 is equal to 0, and the carry out is going to be 0. It's important to know that for a binary number x, if we want to represent it using n bits, then for the unsigned range, x is going to be between 0 and 2 to the power of n minus 1. Now for signed range, now we will split the representation between negative number and positive number, and x at this time will be between minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. Here's an example, 4-bit example. If we see here, we consider 4 bits starting from 0, 0, 0, 0, and then moving through the circle in a clockwise direction to 1, 1, 1, 1. If we assume the signed range for the 4 bits, then we need to split this circle into 3 parts. The 0, and that's an obvious choice. 0 will be 0, 0, 0, 0. And then after that, moving to this direction, we will start having positive 1, positive 2, 3, 4, 5, 6, up to positive 7. So 7 would be 1, 1, 1, 0. Now for the negative side, we will, starting from 0 going to this direction, it will be minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and minus 7, minus 8. And as you can see, we choose this one, so we have like plus 1 in the right and minus 1 on the left. But the representation for the plus 1 is 1, 0, 0, 0, and for the minus 1, all ones. And if you can notice here in the positive, we have from +1 to +7. But for the negative, we have from -1 to -8. So we have one more representation, more than the positive side. And this is why for 4-bit, x would be from -8 to 7. Now, if you choose to use unsigned range, then this is simply going, the positive number is going to be the same, but you will continue after this. This would be 9, 10, 11, 12, 13, 14, 15, and 16. But instead of using the decimal representations after 9, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. After this, we have A, B, C, D, E, and end with F. Now, you can see that the range for the unsigned numbers, if they are 4 bits, it's going to be between 0 and 50. So we have 16 different combination of bits if we use 4 bits. Now, moving to the integer subtraction, there's so many details about the subtraction, and surely you study this before in the logic design course. But as a conclusion, we convert the subtraction to addition by getting the 2's complement of the second operand. This is an example. If it is 7 minus 6, so the subtraction will be converted to addition, and the sign of the number 6 would be -6. So you are adding now 7 to -6. So in this example, the minus is 7, 1, 1, 1, and zeros. The subtrahend is 0, 1, 1, 0, 0, 0. What we do is we keep this the same, the first operand. So we kept it the same here. It is 1, 1, 1, 0, 0, 0. And we change, or we take the 2's complement of the second operand. To take the 2's complement, you start from the rightmost bit position, and then you look for the first one. You copy until you reach the first one. So you copy the 0, and then we reach the first one, and we copied it. After that, you flip every bit. So the 1 would be 0, the 0 would be 1, the 0 would be 1, and the 0 would be 1. And now we can do the addition similar to the previous slide. 0 plus 1 plus 0. Now I took the part that you carry to the next position. I added directly. 0 plus 1 plus 0 is 1, carry 0. 0 plus 1 plus 1 is 0, carry 1. 1 plus 1 plus 0 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. And 1 plus 0 plus 1 is 0. And the carry out is 1. And you can see that 7 minus 6 is 1. So in this calculation, we drop the carry out. Just to remind more in general about addition, if you have 2 ones that you need to add together, then the result would be 0 and a carry of 1. Notice that 0 or 1 plus 1 is equal to 2, but in binary, they would be 0 and 1, like this. This is in binary. So what we do, if you have 1 plus 1, we do the same as this one, but we keep the sum 0, and the carry to the next bit position is going to be 1. Similarly, if you have 1 plus 1 plus 1, that's 3 in decimal, which is in binary 1, 1. So what we do is 1 plus 1 plus 1 is equal to 1 and carry 1 in the next position. If you remember this, you will get the add or the addition, the binary addition correct every time. Okay. So after we revisited the addition and the subtraction, we'll look at the integer addition overflow. The overflow, if the result is cannot be represented using the number of bits specified, and this happens if you add two positive operands and the result is negative. So this will cause an overflow. Similarly, if you add two negative number and you found out that the result is positive, which is unexpected, and this is because of the overflow. These are the two cases of the overflow for the integer addition. And if you add two numbers, one of them is positive and the other is negative, there will be no overflow. Now, it's important to know that the positive number, or if you have a positive number or a negative number, you directly know this from the most significant bit. If the most significant bit is 1, then the number is negative. If the most significant bit is 1, then the number is negative. If the most significant bit is 0, then the number is positive. And here are two examples. You can see in the first example on the left side, we added 7 plus 6, two positive numbers indicated by the 0 at the end. And we assume here 4-bit binary representation. And you add 7 plus 6. When you add it, 1 plus 0 is 1, carry 0. 0 plus 1 is 0, carry 1. 1 plus 1 is 1, carry 1. And 1 plus 0 is 1, carry 0. And now this 0 will be dropped here as a carry output, or it would be in the carry out. But this is the number that you got. And you can see the 4-bit, using the 4-bit representation, that this is a positive number, this is a positive number, and here we have a negative number. This negative number is actually, if you want to know the value, you can do the 2's complement, which is 1. The first one you keep it, and then after that you flip. So you keep this one, and you flip 1, 0, 0. So that's 3. Which means that this number is negative 3. So you can say that 7, the decimal number 7, plus the decimal number 6 is equal to the negative number 3. This is obviously incorrect. And we got this incorrect result because of the overflow. And the reason is, we know that 7 plus 6 should be 13. But 13 cannot be represented in 4 bits. The largest positive number, as we said, is positive 7. And that's the reason for the overflow. Now, how about the second example here? We did the addition, the binary addition for two negative numbers, -7 and -6. Notice that this is 7 and this is 6. So if you get -7, you keep the first one and you flip the rest, as you can see here. Similarly for the 6, you start from the right, you keep the 0. This is the first one, you keep both, and then you start flipping after that to get the -6. Now these are the binary representation for the -7 and the -6. We add 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. And you notice that there was no carries. The carries all the time is 0. The last bit position is 1 plus 1, which is equal 0. And then you have a carry out 1, which we drop for 4 bits. We only can represent 4 bits. And you can see here that this is a negative number. This is a negative number. And here is a positive number. And for the same reason, -7 plus -6 should be -13 or -13. However, we cannot represent -13 because the lowest negative number, or I mean the largest magnitude negative number, is -8. So we cannot represent the -13, and this is why we had an overflow. Now, how to detect the overflow quickly? You check the carry out of the last 2-bit positions. In our case, we used 4-bit. So we get C4 and C3. This is C4 and C3. You notice when you have an overflow that they differ. And we know that the logic gate that can help us with this, when the inputs differ, the output is going to be 1. If we assume only 2 inputs and we generate the truth table, and we have the Cn and Cn minus 1. In our case, it's going to be C4 and C3. Either they are, these are the 4 different combinations. And we want, if they differ, we generate 1. Otherwise, we will generate 0. And we know that this is the XOR gate. So if we XOR Cn XOR Cn minus 1, then this is going to be V, indicating that there is an overflow. We do the same now for the subtraction overflow. Now, the overflow happens if you have positive, you subtracted positive from negative, and you got a negative. Or you subtracted negative from positive, and you got a positive. Those cases will cause an overflow. So remember those cases quickly for the subtraction. The result, if you don't need an overflow, if you want to make sure that there is no overflow, you check the signs of the result and you match it with the first operand. If they differ, then there will be an overflow. Similarly here, there will be an overflow. The other cases, when you subtracted 2 positive numbers or 2 negative numbers, there will be no overflow. And similarly, as we did in the addition, we will do in the subtraction. If we subtracted a positive 7 from negative 6, now the result that we will get at the end is negative 3, which is not matching the first operand. How did we get this result? We simply did what we just learned. We converted the second operand to its 2 complement, and we changed the subtraction to addition. So now the minus 6 is going to be 6, and then we do the addition, and we got minus 3, which is the different sign from the first operand. So this is this case, and this will cause an overflow for same reasons. If we subtract minus 7 from 6, what we did is we converted the subtraction to addition, and the 6 we change it to the negative 6 by the taking the 2's complement. You notice 0, 1, 1, 0 is going to be 0, 1. We copied it, and then we flipped after that 0, 1, 1. And then we did the addition, and we had 3 at the result. And you can see same observation. This is positive, and the first operand is negative. This also causes an overflow for the subtraction. And we notice the same thing again. The carries, the C4 and C3 are different than each other, which means that we can get the same overflow detection of the addition to also detect overflow in the subtraction. And this is good news. We can use the same circuit, which is a simple XOR gate between the carry out and the carry out of the previous stage, XOR them together, and you get the overflow detection bit. Now, dealing with overflow. Now, if an overflow happens, what should we do? Some languages like the C language, they just ignore the overflow. Meaning, in hardware, you just detect that there is an overflow and you don't do anything regarding that, which means that the software programmer should keep in mind that there is certain representation that he cannot exceed. So if you use in MIPS, add unsigned, add unsigned immediate, subtract unsigned, or any kind of arithmetic instructions that could generate an overflow for you, you should be careful not to exceed the representation. In other languages, they do more than just ignoring. They raise an exception. So if an instruction had an overflow, it invoke an exception handler and do other things to react to this overflow. Like they save the break program counting in an exception program counter called EPC, exception program counter, and then you jump to a predefined handler address that has an interrupt service routine that handles the overflow, and you use the MFC0, move from coprocessor register number 0 instruction, which can retrieve this EBC that you save it at the beginning to return after you finish the interrupt service routine, and then you continue after you handled this overflow. Now, we will talk a little bit about the arithmetic for multimedia before going to multiplication. Know that graphics and media processing operates on vectors. Usually, these vectors could be 8-bit, 16-bit data, and notice the usage of power of 2 numbers. If you want to use 64-bit computer, meaning that you will use 64-bit adder, you might use the partitioned carry chain that operates in 8 vectors, each one of them is 8-bit, or 4 vectors, each one of them is 16-bit, or 2 vector, I mean 2 long vector, each one of them is 32-bit. And you notice that the result of this partitioning is always going to be end up with 64 bits. And based on the partitioning that you choose, you use what they call a single instruction multiple data, which is SIMD. So you have a single instruction that works on all the vectors at one time in parallel. You also should be aware of the saturating operation. In case of an overflow, now the result is the largest represented value. So if there is an overflow that happens in a multimedia, like an audio or video, what happens is you give the largest representable number and you say that this is the result. This is contrary to the 2's complement, a modulo arithmetic, where if you, let's say that you have a modulo for 2 bits, so let's say that you have a counter, so you started from 0, 0, and after that 1, 0, going to 1, and then going to 2, and then going to 3. If it is 2 bits modulo, you go back again to 0, 0, and keep counting this way. However, for multimedia, when you reach the largest number, you get saturated there, or you stuck there, you don't go back to the 0, 0. And this what happens if you noticed a clipping in an audio or saturation in video, like certain quality that you cannot go beyond it. This is because of this overflow handling of the multimedia operation. Now going to multiplication. After we finish the addition and subtraction, Now the multiplication, you start with long multiplication approach. We will show this for you, and then we will discuss other approaches that could be having an advantage, especially toward performance. In MIPS, we have 32-bit multiplicand, which is extended to 64-bit by filling zeros to the left of the number. And this is because for the first hardware, we will use 64-bit ALU. And since we use 64-bit ALU that have an adder inside it, it's expecting 64-bit inputs. So if the multiplicand is only 32-bit, because we said that all the registers of the MIPS is 32-bit, why? What happens here is we are going to extend zeros to the left. Now, you should know that we will use in this architecture that we are going to discuss 1 clock cycle per partial product addition. And to understand what we mean by this, here's a very simple example of multiplication where this is the multiplier and this one is the multiplicand. As you can see, we have the decimal value 9, as the multiplier, and we have 8 as the multiplicand. And if you do the multiplication, you generate the partial product the same way that you use in long multiplication approach that we studied in the elementary school. But here it's actually easier, because if you have 1 in the multiplier, you copy the multiplicand here. If you have 0, you 0 everything. If you have 0, you 0 everything. If you have 1, you copy the multiplicand. And then after you generated the partial product, which is actually it's going to be either the multiplicand or zeros, but there is also a shift. Now, after that, you do the addition. You have 0 here, you have also 0 here, and here you have 0, you have 1, and here 0, and here 0, and here you have 1. And as you all know, that 8 times 9 is equal to 72, and this is represented by this binary bits, which is going to be, here we have 64, and here we have 8, and you know 64 plus 8 is going to be 72. Now, if we use 4 bits for the multiplicand and the multiplier also 4 bits, then you should expect that the product is going to be 4 plus 4, which is going to be 8. So the length of the product is the sum of the operand length, meaning the sum of the number of bits in the multiplicand and the multiplier. Now, this is the hardware that is going to emulate this multiplication operation. Now, to understand this hardware, we initially have zeros in the product. And then we start this algorithm by testing the least significant bit of the multiplier that we copy it here. Notice that we have a register for the multiplier, and we have another register for the multiplicand, and the result is going to be the register that is called the product, and we use a 64-bit ALU to do the addition of the partial products. And all these operations is having a control unit that you can build using a finite state machine. It's a sequential circuit actually that controls the registers and the ALU. Now, you noticed in the partial product, we have a shifting mechanism. We shift the partial product somehow. So the equivalent of this in the hardware, we shift left the multiplicand and we shift right the multiplier. We shift right the multiplier because we want to know what's the least significant bit. This will help us to test. If the multiplier bit is equal to 1, which means that I need to have the multiplicand, so I need to add the multiplicand to the running sum in the product. And then after that, I can shift the multiplicand to the left, this side, by 1 bit. If the multiplier bit is 0, I don't add the multiplicand, there is no operation. I directly go and shift the multiplicand to the right. And then I get the next bit of the multiplier by shifting the multiplier register to the right by 1 bit and check, did I finish the binary bit specified for my operation? And we know in MIPS we have 32 bits. So I check, is there 30-second repetition? If there are 32 repetitions, then I'm done. If no, then go to the next bit and do the same. This is the idea of the hardware. And to see this hardware running, here's an example. This is the multiplication if we assume 4-bit version. Now, let's go back for a while. We know that we use 64-bit ALU, which means that I need the multiplicand to be 64 bits. I need also the product register to be 64 bits. So the second operating, because I'm doing a running sum here, it should be also 64 bits. But you should be also aware that there was gonna be a possible carry out, but we're not gonna focus on that at this point. And the multiplier, we use 32 bits, and we always shift it to the right to check the least significant bit, should we continue or not, because we need to do 32 repetition. We have only 32 bits in the multiplier. Now, you can see in this flow chart that there is a decision, and I need to either add the multiplicand or I don't add the multiplicand, which means that there is no operation, and I shift this to the multiplicand to the left, I shift here, or shift the multiplier to the right. The one who's responsible to do this is the control test, and you can see that it has the input, which is the least significant bit of the multiplier. It goes to the control test, and based on that, it tells the multiplier to shift to the right, it tells the multiplicand to shift to the left, and tells the adder to do the add operation, and it tells the product to either add the multiplicand or do no operation. That tells this to the ALU and write the result in the product by allowing the right bit or the right enable digit of the product register. Now, here's an example. If we use the 4 bits, then the equivalent of this hardware here is going to be 8-bit, because we know that the product is going to be 4-bit plus 4-bit, which is 8-bit. So this should be an 8-bit to the multiplicand, and the ALU is with, or the ALU operand is 8-bit, so the ALU should be long enough for doing the addition of 8-bit operands, so it should be 8-bit ALU as well. And the multiplier is only 4-bit. So what happens here, we will do this operation for 2 times 3, and we know that the result is going to be 6. Now what happens is, first, in step 0, we do the initialization. Since we have 4 bits, we need 4 more steps, because every partial product needs 1 clock cycle to finalize. So we need 4 more steps. We have step 0s, we only initialize value. So we know that this is the multiplicand, And we put the multiplied right here, and notice that we extend 4 zeros to the left. And we zero out the product, which is 8 zeros, and the multiplier 1100, we put it right here. I added those arrows to remind you of the shifting direction. So now what happens in the first step, you check the left or the rightmost bit, which is the least significant bit of the multiplier. Since the least significant bit of the multiplier is 1, you add the product, or you add the multiplicand to run the running sum inside the product. And you should also shift left the multiplicand this direction by 1 bit, and shift right the multiplier by another bit. So you should do those 3 operations in step number 1. Right now, we didn't do them yet. In the next slide, we will see the change on the registers. Since the product is 0, because we just began. In step 1, we will add the multiplicand to the product, because this multiplier bit is 1. So this is supposed to be 0, 1, 0, 0, 0, 0, 0, 0 after we do the operation. And then we shift this number to the left and the multiplier to the right. And this is exactly what happened in the next slide. We did the 4 operation, and you notice now the running sum have the multiplicand. And after we generate the multiplicand, we shift this one to the left, and we shift this one to the right. Now in step 2, we notice that we have 1 in the left significant, or the least significant bit. And because we have 1, we do the same for operation. We add the multiplicand to the running sum, we shift left the multiplicand, and we shift right the multiplier. So now we already have this number in the product, and we need to add the multiplicand to the running product. And you can notice that there is a 1 here that should be here in the, after you do those 3 operations, and then you do this shift and this shift, and this is exactly what we did in the next slide. Now the product have 0, 1, 1, 0, 0, 0, 0, 0, and we shift the multiplicand to the left and the multiplier to the right. And this is step number 2. Now we need 2 more steps. Step number 3, we notice there is a 0 in the left, or the least significant bit. And because this is 0, we don't add the multiplicand. There is no operation. We just shift left the multiplicand and shift right the multiplier. There will be no change in the product. So this will happen after we do those 3 operations. And you can see that there is only shifting in the multiplicand and the multiplier registers. The last step, which is step number 4, we check this one. This bit is 0. And because the least significant bit is 0, there is no operation, and we only have shifting. And this what happens exactly and after we did these 3 operations in step number 4. This what happens in the registers. So now the multiplier register should have zeros, because you shift out all the multiplier bits and you check every one of them. And the multiplicand, originally the multiplicand, which is this number, it was here. So at the end, it's all shifted to the left right here. And whatever result, you will have it in the product register. And this is correct because it's matching what we expected, which is the number, or the decimal number 6. Now, these operations, instead of doing this step by step through these slides, we have all the operations in one slide in this table. So this table is multiplying the binary number 2 as the multiplicand and as the multiplier, and the sorry, this is the this is the multiplicand, and this is the multiplier. And you know that the multiplication operation is actually commutative. Now, this is the initial. So we have the multiplier, the multiplicand, and the product. And we initially have the product as zeros. The multiplicand have the multiplicand 4 bits here and zeros here. And the multiplier is the 4 bits of the multiplier. We copied it here. And you notice, you can go through them. This is exactly what we explained in the previous slide, but I'll look at it from a different angle. Now, in the multiplier column here, you can see that it's copied until we have the shift right of the multiplier. So it shifted to the right. And then copied again, and then you shift to the right. Copied again, and then shift to right. You shift to the to shift to the right, and again you copied it and shift to the right, and then you copy it and then shift to the right. So you can actually generate this column without looking at any other columns. Similarly for the multiplicand, you begin this way and then add this operation, which is operation number 2 of every stage or every step. You do the left shift. So we do the left shift here, and then we copy it, left shift, and then we copy it, left shift, and we copy it, and so on. Now, in the product, you start with zeros, and you only do the addition, or you add the multiplicand to the product only if you have the multiplier bit equal to 1. As you can see, this is in step 1 and step 2. The other 2 steps, it's just 0, so you don't do any operation. There should be no operation here and no operation. Now, the product starts with zeros. Here we added the multiplicand. So we add this to the running product, which is this one. You can also say that you add to this step, you add those 2 together. Again, to do this step, you add those 2 together. Now, to do this step, there is no operation. So you just copy it. Similarly here, there is no operation. So you just copy it. Now, this architecture that we discussed is actually the non-optimized multiplier, where we need 3 registers, 64-bit for the product, 64-bit for the multiplicand, and 32-bit for the multiplier. We also, in every step along the way, we need to do 2 shifts. We shift left the multiplicand, and we shift right the multiplier. And because of the 64-bit of the product and the multiplicand, we need 64-bit AL. Now, we can optimize this hardware to this one, which you can see is getting smaller. We now need only 2 registers. We need 64-bit product here, and we need only the 32-bit multiplicand. And we take out the multipliers altogether. We take out its register. In the operation, in the shift operation wise, we need to do only shift in the product register. So we shift the product register to the right. And because of this optimization, we now need 32-bit ALU instead of the 64-bit. How is this happening? Because what the big contribution of this hardware, we performed some steps in parallel, namely the add and the shift. We do them together. And to do this, we take out the multiplier altogether, but we initially put the multiplier in the right half of the product. So here at this part, we need to plug in the multiplier. Instead of zeroing out all the product bits, we keep the multiplier here. And this tells you that you need to do shift in the right direction. And every time you get the multiplier bit out, and based on this least significant bit that goes out from here, it tells the control what to do for other hardware parts. Notice that there is nothing you shift in the multiplicand, so it's stationary. The ALU, you either have an add command to do the addition, or there is no add, there is no operation. And also for the 64-bit product, those most significant bits, which is the 32-bit most significant bits, initially they are 0, and the running sum happens only here. It happens only here. Now, we will have the same example as the non-optimized multiplier. In the optimized multiplier, this is the hardware. And if we use a 4-bit example, the ALU is going to be 4-bit. The multiplicand is 4-bit. And we have an 8-bit product. And initially, we have the multiplier here. And we zero out the rest of the upper 4 bits. And those 4 bits are contributing to the running sum. So this is the initial case. This is step 0. And step 0, we put the multiplicand right here, and the multiplier right here, and we zero out the rest of the product. And then since we have 4 bits, we need to do 4 more steps. And then we will go through those 4 steps one by one, as we did in the non-optimizer or the non-optimized multiplier. In step 1, since the least significant bit of the product is 1, now we are looking at the product, there is no more multiplier register. What happens is we add the 4 most significant bits only, which are those zeros representing the running sum. So we add those 4 bits with the multiplicand. So we need to add the multiplicand because we have 1. And after we're done with this, we shift right the product. So what happens is we need, since this is 0, we need to have the multiplicand here. So it should be 0, 1, 0, 0. And then we shift everything together to the right. And this is what happens after we do those 2 operations in the registers, as you can see. There. So here we added first, and then we did the shift of the product. This marks the end of step 1. Step 2, again, we have 1 in the least significant bit of the product. So we do the running sum between those 4 bits in the product and the 4-bit of the multiplicand. You notice if you add those, there will be 1 here. And then after we do the addition, we shift the product to the right. And this is what happens in the next slide. We added first. So there was 1, 1, and then we shifted everything to the right. Now, in the 3rd step, we notice there is a 0. So there is no operation. We don't do any running sum addition. And we just do the shift right of the product. And this is what we did in the next slide. Again, In step 4, it's 0 and the least significant bit of the product. So there is no operation and we just do the shift. And this is exactly what happened in the last step. And you notice that the end result is the same as the expected result. It's going to be 6. Now, this is an optimized of hardware of multiplication that doesn't have a lot of hardware. The hardware is very simple compared to the previous one, but still it needs a cycle for every partial product operation. Now, the same thing that we just explained to you is recorded in a table format. This is the step 0, which is the initialization step. And then you have 4 more steps. The first 2 have 1 in the multiplier, in the product. And the last 2, you have zeros. Here we show only the product since the multiplicand, which is this number, never changed. So we just keep it and we copied it first. Sorry, this is the multiplicand. We copied the multiplier here at the beginning, and the multiplicand is the one we add to the running sum if there is a 1 in the least significant bit of the product. And this is exactly what happens in these steps. It's the same as we explained in the previous few slides. So in summary, we check this bit. If it is 1, you add here, you add this multiplicand, this one with the 0, and you generate this value, and then you shift everything to the right. And you can see that we shift. And then again, we have 1. So you need to add, which means that you add this number for the product right here with the multiplicand, and you have 1, 1, 0, 0, and then you do the shift. Similarly here, but now in the last 2 stages, we have zeros in the least significant bit of the product. So there is no operation, and you just keep shifting to the right, and you generate at the end the same result. Now, the previous 2 hardwares are doing shift and add operation to do the multiplication. So it is shift and add that needs many cycles to finish. There are faster array multipliers. Now here's an example of a 6-bit array multiplications where you have 2 binary numbers. Each one of them is 6 bits, and these are the partial products. And you notice that for any partial products, let's take this one for example, it's actually the bit of the partial product is a symbol and gate, where you take the x, the respective x and y bits, being xn and ym, xn and ym, and you add them together. If there is a 0 in the x, the result would be 0. If it is 1, then it's going to be the y. So it's just symbol and operation for each one of them. What happens now in the hardware, this is one way to organize the array multiplier. This is called also a parallel multiplier. And it's a direct implementation of the partial products with the shift and everything. So you can notice the first one here, x0, ANDed with y0, it goes directly to the partial product 0. And this is what happens here. Now the second one, you need to add those 2 bits. And to add them, you use a full adder where you need 3 bits. These are 2 bits, and you need one of them is going to be a carry n of 0. And then you generate the partial product. For the next column, you need 3 bits. So you have those 3 bits, and you also have possible carries from the previous stage. So what happens? You see this one, you take those 2, you add them together. This is being the x0, y2, and this one being the x1, y1. And then you get the addition, and this sum is added to x2, y0. x2, y0. Now for this two full adders to work on and get you the partial product bit P2, then you need a carry n here of 0. And similar thing for the other bits. You can build this hardware easily by copying this row here. You copy the next row right here. And you continue copying the rows one by one. And you can see that every time we shift to the left. You also notice that because this is the first full adder in every row, we have a carry n of 0. And while you are building, you will notice also that this adder, this specific adder, it will have only this bit, and it needs another operand, which is going to be 0. And it will generate a carry out for you that's going to be the carry n in the next, or the first operand in the next row. So the carry out here is the second operand, the carry out is the second operand, and so on. And this way you generate the partial product from P0 to P11. From P0 to P11. Again, since this is 6-bit and this is 6-bit, then the partial product should be 12, from 0 to 11. Now, there is another implementation of the same array multiplier, and I think the idea is easy for you. The other idea is to do it this way. Notice that now we copy the first row, which is this one, right here. The second row is right here. Now what happened in this implementation, you will notice that every row, you are missing an adder if you compare it to the first slide for each row. And at the end, you have those collective adders as another last stage. Now, to use this implementation, what happens here is you get the 2 bits, and in the first row, you insert a carry n of 0 everywhere. And then the carry out is going to be going to the carry in of the next row. The carry out here, the carry out to the next one, the carry out to the next one, and so on. So, comparing this to the first, we have the zeros in the carry in of the first row, and this we have another adders here in the last stage, and we take out the adders that they were here. In this adder, the new line, we have to add a 0, right? As a carry. Let's compare between this and the previous slide. This is the previous slide, and this is the next slide. And you can see what I mean. Now, you notice that there are missing adders here, but there is a new line of full adders right at the end. Again, this is the previous slide, and this is the next slide. So this is equivalent also to adding the zeros here in the carry n, and the 0 here when you're trying to generate P6, which is in the middle, right in the middle of the partial product bits. So there are two different implementation of the parallel adder. If you want to look at them again, here for every row, there is a rippling for every row. So the carry out is the carry in of the next one. The carry out is the carry in of the next one, and so on. Now for the next one here, the rippling happens diagonally. So this rippling happens this way. So that's the main difference between the two implementation. Now, in the MIPS ISA, we have the multiplication instruction, where you have two 32-bit registers for the product. You have high and low. High is the most significant 32-bit, and low is the least significant 32-bit. The instruction is called mult. That's if RS, which is the source, and the two source registers, the two operands, if they are signed number. If they are unsigned, you can use the mult unsigned. Now, we define the high and low because now we know if we use 32-bit register that is already defined in the MIPS, as we explained in the previous video. But the destination of the multiplication, it needs to be 64-bit. So we need to combine the high and low of the results. To do this, we have those two instructions, which is move from high and move from low. So you have the destination register and you move the high and low, so you can get the result as 64-bit. You can test the high value to see if the product overflow also, if you have more bits. This is in case of the overflow. There is also this instruction, which is called mul, RD, RS, and RT. The least significant 32-bit of the product only going to be an RD. So you'll generate only the least significant 32-bit. Because remember, if you have 32-bit operand and you want it to multiply it by another 32-bit operand, the result would be 64 bits. And also you should read your textbooks. There is a possibility of a carry out. Anyway, let's say there are 64 bits. If you use this instruction, then the result in the destination is going to be only the least significant 32-bit. Now, after we know the instructions in the multiplication and the discussion, so just to remind you, we use an optimized hardware where you do add and shift with many cycles. And then we optimize the same hardware. We used a simpler hardware. And after that, we discussed the faster parallel multipliers. And also we checked what are the instructions related to multiplication in the MIPS. Now we will do the same for division. Now for the division, we know the old way, the long division that we studied in the elementary school. In the binary, what we have here, we have the divisor here. We have the dividend right here. And we have the quotient. And after we finish the operation of the division, we end up with remainder. So what happens here, first you need to check the divisor. Make sure it's not 0. So a 0 divisor is not allowed. You know, division by 0 is not allowed. The long division approach, what happens here, you check if the divisor is less than the dividend bits. If the divisor is less than the dividend bits, you have 1 bit in the quotient, and you do the subtraction. Otherwise, there will be a 0 bit in the quotient, and you bring down the next dividend bit and try again. Now, to do this division, we have a restoring division where you do the subtract, because to know if the divisor is less than the dividend, to do it, you subtract, and if the remainder goes or less than 0, meaning the end remainder in the stages after you do the subtraction, if this one is less than 0, meaning it's negative. And we know that if there is a negative number, the most significant bit of that number is going to be 1. So if we see a negative in the most significant, we restore the divisor back, meaning that this subtraction is not doing the job. So we add the divisor back to restore it to its original. And we try by having more bits from the dividend. This is a sign division. You divide using an absolute value and then adjust the sign of the quotient and the remainder as required. Because, you know, in the multiplication, if you multiply positive with positive, it's going to be a positive number. If you multiply positive with negative, it's going to be negative. Similar thing in the division. Now, let's try to understand this. What happens is you begin, this is the divisor, this is the dividend. And first you try, if you have only 1 bit, and this is not going to be enough, for sure. You add 1 more bit, it's not going to be enough. Add 1 more bit, it's not going to be enough. Until you copy the same number of bits as the divisor. So basically, you should start with 0, 0, 0, 1. You copy it here, 0, 0, 0, 1. Now you subtract. You notice that this is 9 and this is 8. If you subtract, then you will have 1. You will have 1. And you know it's going to be 1, 0, 0, 0. And here, this is a positive number. So this subtraction was good for us. What happened? We know that this is okay. We put 1 in the quotient, and then we drop the next dividend bit. And we try again. We know that this is not enough. We need 4 bits. So what happens is we add 0 and then drop the next bit. Not 4 yet. It's not 4 bit yet. So you add 0 in the quotient and you drop the next bit. And now you have 4 bits. Now what happens now, since you have 4 bits, you could put 1, and 1 multiplied by those numbers is you copy the same divisor here, 0, 0, 0, 1, and now you do the subtraction. Luckily, this time is also okay, because this number is A or 10, and this number is 8, so it generates the final remainder, which is 2. So this is the old way, but in the old way of division, but using binary numbers. Now, to do the division in hardware, we use this hardware, and if you look carefully, you'll see that it's very similar to the multiplication. The main difference is here. First, the shifting is opposite directions. This is going to be the divisor. This is going to be the quotient. And here you will get the running result, which is the remainder. Again, we use 64-bit. This is going to be 64, and the remainder is going to be 64-bit. For the quotient, notice that we shift in the opposite directions, And here in the output of the quotient, previously in the multiplication, you see what is the left or the least significant bit, and based on it, it goes to the control to check what the operation that we should do. But here in the divisor, in the division, I mean, we use the remainder. And we check what is the most significant bit of the remainder. So in the multiplication, we check the least significant bit of the multiplier that was here. But in the division, we check the most significant bit of the remainder. So we check the bit here to know if the result here is negative or not. To understand this better, you should know at the beginning, we put the divisor in the left half. So we put the divisor here in the left half. This is 64 bit. We put 32 bit of the divisor here, and we zero out the right side. It's the opposite of the multiplicand. If you go to the multiplicand, you will check that, you will find that this is the opposite. And in the quotients, initially we put it at 0, and we start to fill them bit by bit by shifting to the left. So you put the new bit and then shift to the left. For the remainder, it has the decision bit, which is the most significant of the remainder. Initially, you put the dividend bits here, which is supposed to be 64 bits. So to do this, you start at the beginning. You subtract the divisor register from the remainder register and place the register in the remainder register. So notice what you do here. At the beginning, you subtract. You subtract the divisor from the remainder. And then you test the result. Is it negative or positive? Here it's going to be positive. Here it's going to be negative. The positive remainder, it means that the subtraction was successful and we can continue. If it is negative, it means that the subtraction was unsuccessful and we need more bits. So let's do the successful one first. If the remainder was positive, then it was successful. You just shift the quotient register to the left. So you continue by shifting this to the left, meaning that I'm getting the new bit. I'm shifting that new bit here, setting the new rightmost bit to 1. So this would be the new rightmost bit that will end up in the quotient. If not, this mean the result is negative. We restore the original value. Notice that we subtracted here, and we got results that were negative. It's unsuccessful. So what to do to go back? We need to add. And this is why we have add and subtract in the ALU. So you restore the original value by adding the divisor register again to the remainder register and placing the sum in the remainder register. So in this stage, you restored the old value. The old value that you have it here in the remainder. And then you also do the same operation that you did here. You shift the quotient register to the left, setting the new least significant bit to 0, meaning that since if we succeeded, this means that the quotient bit should be 1. If we failed, then the quotient bit is 0 and get the new bit by shifting the divisor register right by 1 bit. So you shift this by 1 bit. And then you check if you're done or not. Here we check if we have 33 repetition. So if you have 32 operand, you would do 33 iterations. If you have, for example, 4 bits, and you want to do the division, then you need to do 5 steps. If 4 bits operand, then you do 5 steps. If the divisor, namely, is 4 bit. So that's basically what happens in the division, and we will test it using the table. You can do the same one that we use in the multiplication step by step in the hardware, but I did it directly in the table. So initially, we want to divide 7 by 2. So we know that 7 by 2, the result in the quotient should be 3, and the remainder should be 1. So what happened? The quotient at the beginning is zeros. The divisor is going to be at the leftmost 4-bit, which is the 2. Should be here. And the least significant 4 bits of the divisor is going to be zeros. The remainder, at the beginning, we initially have the remainder as the dividend bits, which is 1, 1, 1, 0 here in the least significant bit, and the rest we extend it with zeros. Now what you do after the initial, you subtract and check if the subtraction is okay or not. You subtract the remainder being the first operand and the divisor being the second operand. So you can see that the divisor here and the remainder here, the divisor is clearly bigger than the remainder. So if you subtract the first operand from the second operand, this is going to be the first operand, and this is the second operand. Since the second operand is bigger than the first, the result must be negative. You can do the subtraction. Of course, you do the subtraction by taking the 2's complement of the divisor and then add, and you get this result. Actually, those bits for us here is not important. We know from the get-go that this is going to be a negative number. So since this is a negative number, meaning that the remainder is less than 0, then we need to restore back the remainder by adding the divisor. So notice that we started with this one. Then after we did the subtraction, we got negative result. And here we restore it back by adding the divisor again. Now, at the same time, we shift left logical to the quotient. So the quotient is shifted to the left by adding a 0 to the least significant bit. So you added 0 here. And we added 0 because we failed. So the new quotient bit is going to be 0. And after that, we shift right the divisor. And this is what happens here, as you can see. Now we did again, and this is the first step, we finished it. We do the same thing for the second, and you notice that still the divisor, even though we are shifting the divisor to the right, still it's big. It's bigger than the remainder. So the subtraction will give us also negative. And because of this, we restore back and then shift this one to the left by adding 0 at the end. And we shift right the divisor. So at this point here, we finished the second stage. And you can notice that every time we are reducing the divisor value, hoping that after we do the subtraction, we will get a result that is not negative. Now in stage number 3, again, this divisor is bigger than the remainder, but you can see that they are close. This is 8 and this is 7, and this is why after we subtracted 7 minus 8, the result is -1. So it's negative, and because it's negative, we failed. We restore this back, and we shift to the left and shift to the right. Now we start succeeding at this point in the fourth stage. What happens? We will try the subtraction, and you noticed here that the divisor is less than the remainder. So 7 minus 4 is going to be 3. This is positive. And since the remainder is positive, you don't restore, you keep this. This is a good remainder for us, and we can continue. And because this is successful, now the quotient bit, the new bit that we are shifting to the quotient left with is 1, because we succeed. And you shift right the divisor to the right to redo this again, and this is the comparison between the subtraction between the remainder and the divisor. You can see that this is 3, and this one is 2. So the subtraction is going to be 1. The subtraction is going to be 1. And this is telling you this is a positive number, meaning that it's successful. You don't restore. You give 1 to the quotient and shift it to the left. And you shift right the divisor, marking the last stage. Now you see the remainder equals to 1, and the quotient is equal to 3, and this is what we expected. 7 divided by 2 is 3, and the remainder of 1. The optimized divider, it still have 1 cycle per partial remainder subtraction. It looks like looks a lot like the multiplier. It has you can actually use the same hardware, but you should notice that now in the remainder you can shift it to the right and also to the left, because you see in the operation that there is a decision. Sometimes we shift to the right, sometimes we shift to the left. Still, we are checking the most significant bit, and we feed it to the control finite state machine. And now the quotient, instead of register by instead of saving it in a register by itself, we put it in the right-hand side of the remainder. Now you notice that the remainder, you should notice that the divisor is 32-bit, the remainder register is 64-bit, and we do the running operation, whether it's subtraction or addition for restoring purposes, is happening in the 32 most significant bits. So as a key difference between the optimized divider and the optimized subtractor, the optimized multiplier, the shifting here happens in both ways, to the left and also to the right. And for the faster division, you think that we can do a parallel division like what we did in the multiplier, but we cannot do that for the division. The subtraction is a conditional on the sign of the remainder. The faster dividers, using another method called the SRT division, it generates multiple quotient bits per step, and you can do somehow the parallel or an equivalent to the parallel hardware, but this subject is actually a master level subject in computer arithmetic, so we will leave it out. So know that there is a faster way that's called an SRT division, and this is also you should know that this is implemented in the simple calculators that you have in your hand. Now, for the MIPS instructions, the MIPS division uses again the high-low registers for the result. The high would be 32-bit remainder. The low is 32-bit quotient. Now the dividend needed a 64-bit. This is why you have these instructions. You have divide or div, RS and RT. You have div unsigned, RS, RT. There is no overflow or divide by zero checking, so you should be careful. You should manage this by your algorithm itself. You can also use those two instructions that we defined for multiplication, move from the high and move from the low to access the 64 results. Now, at this point, we finished the first part. We said in this chapter, we will focus on the arithmetics as the first major point, and now we finished it. And the second part would be the floating point representation for the non-integral number. So we will check the floating point representation, meaning how to represent a float or a double number that you define in your high-level language. After we know this, the representation, we will check how to add and multiply floating point numbers, but this would be the subject of the next video.